Now we will see how to calculate the inductance for the transmission line. We are having many forms of transmission networks. In case of single phase, we are having single phase single circuit, single phase double circuit, three phase single circuit, and three phase double circuit. For these all transmission lines, we have to calculate the inductance, and then we can go for analyzing the transmission network. Say for example, single phase single circuit means it should be somewhat like we know very well single phase we are having phase and neutral, so we have to assume two conductors for this one, and the distance separated between the two conductors is d meters. For double circuit, it's simply a four conductors arranged either in the form of square or rectangular, or even it may be all the conductors may be in horizontal or vertical, in any form, depends upon the structure of the transmission network. The three-phase conductor. So this is somewhat like a equilateral triangle. The distance among the conductors are all same on all the sides. Also, it's possible to make your three-phase single circuit in the form of uneven distance. So this one we are calling it as unsymmetrical spacing. So if you see here, this conductor 1, 2, 3 are all not at same distance, all are different. Why we have to especially concentrate on these two? Yes, because of this distance your inductance may vary. I think 1 second, I want to show that one, because if you see the equation here, all the equations are depends upon the distance among the conductors. So definitely that plays an important role for the magnitude of inductance formation in the transmission network. In the same way, finally we have to calculate the inductance for three-phase double circuit also. Double circuits means it will be like this. 6 conductors will be there, A, B, C, and A dash, B dash, C dash, or otherwise the form may be in this form also, uneven distance. It's not mandatory again, it should be in the hexagonal form, or it may be in the horizontal, or it may be in the vertical also. First, we will go for calculating the inductance for single phase single circuit transmission line. For this, just consider a single phase single circuit transmission line of conductors A and B. That means for phase as well as for neutral. The radius of each conductor are meters. Spacing between the two conductors is D. The same magnitude of current flows in conductors A and B, but in opposite direction. We know very well that phase currents means in one conductor the current will flow, and in the next conductor the current will come from that place. So that is a return current. So obviously we can say current in conductor A, we can say normally IA, and current in B, current in conductor B is IB. So we can say, since both the magnitudes of currents are same, we can say IA equal to minus IB or minus IA. That means both the conductor magnitudes are same. Yes, we already know that LA equal to psi A by IA. That means this A represents, we are calculating the inductance for conductor A alone. LA equal to psi A by IA. Here this psi A we are going to calculate. Psi A is equal to psi AA plus psi AB. This psi AA denotes the magnetic flux linkage of conductor A because of current IA. That means both magnetic flux linkages, internal flux linkage as well as external flux linkage. This psi AB denotes external magnetic flux linkage of conductor B. That is magnetic flux linkage on conductor A because of current IB. Now this form we can able to write as psi A equal to psi AA internal plus psi AA external plus psi AB. So now you know very well for what are all the expression for all these three terms. Mu naught IA by 8 pi is for internal plus mu naught IA by 2 pi integral of r to infinity dx by x. This complete term is for external flux linkage plus mu naught IB by 2 pi integral of d to infinity dx by x. This is for your external flux linkage because of current IB. So because this, if you see here this term IB as well as D is the distance between the two conductors A and B. Now if we solve this complete equation, if you solve, then we will get the final expression psi A equal to mu naught IA by 2 pi into 1 by 4 plus ln D by R. This ln is the natural logarithm, and while you are integrating here you will get a natural logarithm because dx by x is there, 1 by x, integral of 1 by x is the natural logarithm, and if you apply the limits r to infinity as well as d to infinity, then we will get the solution, final solution like this. Here one thing, while you are solving the thing, you have to understand that here we are having, while you are expanding the equation, and we will get IA plus IB. This IA plus IB is 0, we know, because we are just saying that the current is the return path in neutral, and whatever the magnitude of current flows through the phase current, and the same current is returning back to the neutral wire. So that means IA plus IB is equal to 0. That's why this complete term will vanish. And in place of IB, in order to get the current in terms of IA, we are representing this IB in terms of IA. That's why we already said that IA equal to minus IA. Sorry, IB equal to minus IA. Okay, so that means if we substitute those things in terms of IB, if we substitute IA, then we will get the complete equation in terms of IA. So the total net flux linkage psi A equal to mu naught IA by 2 pi into 1 by 4 plus ln D by R. This is for flux linkage on conductor A because of the current flows in conductor A as well as the current flows in conductor B. Now how to calculate the inductance? Inductance LA equal to psi flux linkage by current flowing through the conductor A, that is IA. So if you solve that one, then final equation we will get mu naught by 2 pi into 1 by 4 plus ln D by R. From this equation we can say that your inductance, it depends upon the distance between the conductor as well as the radius of the conductor. This mu naught represents the material, what type of material we are using for the conductor. So now if you substitute the value for mu naught equal to 4 pi into 10 to the power minus 7. On further, if you want to simplify the final expression, on substituting the mu naught value, we will get LA, that means inductance on conductor A alone is equal to 2 into 10 to the power minus 7 ln D by R. And also we are having here ln, if we take the natural logarithm, if you want to simplify furthermore, this term 1 by 4 we can able to represent ln e to the power e to the power 1 by 4. This again logarithmic equation terms we can able to simplify further. So if we do it, ln D by R e to the power minus 1 by 4. So this term r e to the power minus 1 by 4 we can represent as r dash. That is effective radius of the conductor. Why we have to call it as the effective radius of the conductor? Yes, the meaning is because of skin effect. Your current is not flowing on all the part of the cross section of the conductor. Because of skin effect, the current is only concentrates on the outermost part of the conductor. Because of that, the radius of the conductor on AC supply reduces. So that's why here we are putting this r e to the power minus 1 by 4. That means if we say here, if we saw the value of e to the power minus 1 by 4, that value is 0.7788 of 8 times of radius r. Only 77.88% of radius only we are utilizing due to skin effect in AC side. So this is for conductor A. Now if we are going for loop inductance, because all the loads are connected in parallel, if you want to find out the total net inductance on single circuit, then this two conductors A, B both will be in series, and the net inductance if we calculate, then that will be the twice the time of your inductance on conductor A. That means LAB equal to 2 into LA. So your equation LAB equal to 4 into 10 to the power minus 7 ln D by R dash. Inductance for three-phase single circuit line. As we consider for single phase single circuit, here also we are considering three conductors A, B, C, and their radius or R meters. Also we are considering the balanced load. Practically this is not possible, but for our calculation purpose we are considering we are having a balanced load at the receiving end side, and because of that we are assuming the current flowing through all the conductor, algebraic sum of current flowing through all the conductors IA plus IB plus IC equal to 0. So now we have to come for spacing among the conductors. So while we are thinking about the spacing among the conductors, we may keep the conductors in the transmission line in the form of two. One is spacing among the conductors are equal, and in another case spacings among the conductors are all different. So depends upon these two category, we can call it as unsymmetrical spacing as well as symmetrical spacing. Do the spacing definitely that's make any changes in the inductance? Yes, definitely that makes. Already we have seen in the flux linkage D is also one of the factor. In three phase also we have to categorize, or we have to derive the inductance in two form. One is for symmetrical case as well as another one is for unsymmetrical spacing condition. In case of unsymmetrical case, while solving the equation we have to assume some condition. Why we have to go for transpositioning of conductors? This is nothing but the circuit or arrangement of conductors in the transmission line. Just see this. For a particular session or particular distance, your three phases can be connected in this form. Maybe in position 1 conductor A will be there, and in position 2 conductor B will be there, and in position 3 conductor C will be there. This is for up to particular distance. Again in the next session, in position number 1 your conductor C may be there, and in position 2 conductor A may be there, and in position 3 conductor B will be there. This type of arrangement we can call it as transpositioning of conductors or transpose. Simply we can call it as transpose. Why we have to rearrange these type of three conductors? Yes, as we discussed earlier also, while calculating the inductance of the transmission line, spacing among the conductors is the main one, is the main factor. If we are having unsymmetrical spacing among the conductors, then while you are calculating your inductance, net inductance of the transmission line for each conductors, that means for conductor A, conductor B and conductor C, that may vary. We know very well if the inductance varies among the conductors, definitely the voltage drop on each conductor that also again varies. We are not having a small distance. Our transmission lines are in terms of hundreds of kilometers, and finally at the receiving end side the voltage become unbalanced. The consumer will not get a constant supply. That is, an uneven voltage will be there. In order to avoid this uneven voltage, the formation of inductance in the transmission network should be equal. In order to make the inductance formation equal, or in order to balance the inductance, we are transposing the conductors at regular intervals. So that's why here we are showing session 1, session 2, session 3. In session 1, if you see the conductor arrangement is ABC with their distances are D1, D2, D3, and in the same way in session 2 the conductor arrangement is CAB, and in session 3 the conductor arrangement is BCA. Again in the session 4, if you see, again that repeats the session 1 series, that is ABC. So the one cycle it completes within the 3 sessions. Now we are considering for our equation these 3 sessions, and we have to calculate the inductance of A, conductor A, in session 1, in session 2 and in session 3, and if we simply take the average of these 3 sessions, that's the magnetic flux linkage of conductor A of a particular distance. If we calculate for remaining other 2 conductors B and C, again the same amount of magnetic flux linkage we will get. So in this way we are balancing the inductance for all over the transmission network. This is not for calculation alone, this is for really in practically if uneven distance is there, then the people they are, while erecting the transmission system itself, they are rearranging the conductors in this way in order to equalize the inductance among the conductors, so that at the receiving end we will get the balanced voltage. So while we are solving, we are going to see these terms also. That's why we have written here IA. We know very well IA plus IB plus IC equal to 0, and for unsymmetrical case these 3 terms we are going to substitute in the equation. IA equal to 1 in I into 1 plus J0, IB equal to I into minus 0.5 minus J 0.866, and IC equal to I into minus 0.5 plus J 0.866. These are nothing but your complex term of current equations. Inductance for 3-phase single circuit line for symmetrical spacing. Symmetrical spacing means conductor spacing between the conductors AB, BC, CA are all same, say D meters. So while we are going to see here, again just go for imagine this diagram, and for conductor A to B, B to C, C to A, it may be initially you can consider D1, D2, D3 like that, and this D1 equal to D2 equal to D3 equal to simply D. So like that you can imagine while you are solving the equation. So up to certain part of equation we are going to imagine the distance between the conductor A, B is D1, D2, D3 like that. Then we will substitute in place of D1, D2, D3 simply D. So again come to the equation, consider the conductor A, the inductance on conductor A equal to psi A by Ia, and in order to calculate the flux linkage on conductor A is equal to psi AA plus psi AB plus psi AC. Because we are having three conductors, the total flux linkage equal to flux linkage internal plus external due to current Ia plus flux linkage because of current IB, flux linkage because of current IC. So now if we substitute all the values of flux linkage in equation, then we will get mu naught Ia by 8 pi plus mu naught Ia by 2 pi integral of r to infinity dx by x. This is for internal and this one is for external flux because of current Ia. Now for flux linkage because of current IB, mu naught IB by 2 pi integral of d1 to infinity dx by x plus because of current IC, mu naught IC by 2 pi integral of d2 to infinity dx by x. If you see here, IC is here, that distance is d2, and for IB that distance is d1, that is between the conductor A to B is d1, A to C is d2. Now we have to solve this equation in order to get perfect solution. How to solve this one? If you rearrange this equation, then we will get the equation in terms of natural logarithm. Ln infinity minus Ln r, Ln infinity minus Ln d1, Ln infinity minus Ln d2. Already we know d1 equal to d2 equal to d3 equal to, we are considering d. Simply in place of d1 and d2 we are just putting d here. Now if we expand this equation and if you want to simplify, the next step we can able to get Ln infinity into Ia plus Ib plus Ic. These infinity terms we can commonly take outside and we can just put Ia plus Ib plus Ic in order to simplify. We know that Ia summation of all the three currents are equal to 0, so simply this term will vanish. If this becomes 0, then we reduce the equation somehow. Now the next step what we can do, this distance are all d only, so again these two terms we can able to simplify. These two terms are all because of current IB and IC, so if we take it this Ln d outside, we will get minus IB minus IC. So in place of this minus IB IC, we have to substitute in terms of current A. So once if you substitute, then the final equation we may get mu naught Ia by 2 pi 1 by 4 plus Ln d by r. This is nothing but what we have derived for single equation, single phase single circuit. The same type of equation once again we got for our three phase single circuit also. For L, that is for inductance in conductor A equal to mu naught by 2 pi 1 by 4 plus Ln d by r. This current Ia is cancelled because of while calculating the inductance, and now if we substitute mu naught value here, then we will get 2 into 10 to the power minus 7 Ln d by r e to the power minus 1 by 4. This r e to the power minus 1 by 4, again because of skin effect, the radius, actual radius of the conductor, that will reduce, so that we can call it as effective radius of the conductor, that is r dash. Yes, now we have to come for how to solve for unsymmetrical case. So again for unsymmetrical case, just imagine the three conductors of distance d1, d2, d3, and now we can just see that up to this all the solutions are same. If you see here, the magnetic flux linkage is because of current IA, IB, IC, all we have represented here. Once if we represented all the values here, we have to solve the equation. But while you are solving the equation, we are having different. The distance are all not same here. We know that D1 is not equal to D2, that is not equal to D3. So here the solution, we have to solve these equations somewhat different. And we know in unsymmetrical case, there is a transposition of conductors are there. We have to calculate the inductance for conductor A for session 1, session 2, session 3. That means part 1, part 2, part 3. Finally, we have to take all and we have to average that value. Okay. Now, if we solve this magnetic flux linkage A for session 1, how can we solve this? While you are solving or integrating this equation, then we will get all the term in terms of natural logarithm, and as we know that this IA plus IB plus IC equal to 0, so that term also will vanish, and now your equation will become in terms of IA, IB, IC. In last case, that means for symmetrical case, your distance are all same. So simply we mentioned here D and D, we can commonly take outside, and IB plus IC like that we got. But right now here we can't make it because the distance are all not equal. So we have to keep this D3, D2, D1 as it is in the equation, and instead of this distance, we are going to alter or substitute the current value here. As already in the slide, last slide, we have shown that we have to represent the current. We can represent the current in the form of complex term, so that we are going to substitute here. In place of IA, it's I into 1 plus 0, and in place of IB, it's minus 0.5 minus J 0.866, and for IC it's minus 0.5 plus J 0.866. If these terms, if you substitute in this equation, we will get the final solution for session 1. That means for part 1, psi A1 equal to mu naught I by 2 pi 1 into 1 by 4 plus ln square root of D3 D2 by R plus J 0.866 of ln D3 by D2. So this is for magnetic flux linkage on conductor A in session 1, that means part 1 portion. In the same way, we have to calculate the magnetic flux linkage on 3 portions, session 1, session 2, session 3. If we do like that, then we will get the final equation like this. So here we have represented all the values like LA, LB, LC like that. Instead of that one, you can just imagine this is for LA1, LA2, LA3, all are same only, obviously. And here we derived for psi A, and here already they converted because the current terms we deleted because we consider the current I here. Okay, now here these values, if you go through thoroughly, then this second term you just see ln square root of D2 D3 by R. In the next equation, if you see, this is D3 D1, here D1 D2. In the same way, if you compare all the third terms here, then whatever the term here D2 D3 means here D3 D1 D2, the same terms here it will come. If you sum up all these 3 equations and take the average of that one, finally you will get the solution. The net inductance of each conductor LA equal to LA1 plus LA2 plus LA3 by 3. That means average we are taking. On solving this complete 3 equation, then we will get simply for conductor A it is equal to 2 into 10 to the power minus 7 ln cube root of d1 d2 d3 by r dash. Again, if you see this equation, your natural logarithmic term we are having in the numerator, it's a distance among the conductors by the effective radius. How can we say this is the distance among the conductors? Yes, this is nothing but a geometrical mean distance among the conductors. The cube root of d1 d2 d3 we can call it as simply GMD, geometrical mean distance, and the denominator we can also call it as GM or geometric mean radius. So now if you compare all the three derived inductance equation, we are having 2 into 10 to the power minus 7 ln GMD by GMR. That means in those equation it's simply d by r, and here only for unsymmetrical case it's cube root of distance among the conductors by r dash. In the same way, please try for inductance calculation on single phase double circuit as well as for three phase double circuit line.